I'm Bob Duffy with Intel, and welcome to this Vodcast series on Intel oneAPI and CERN Openlab. In this episode, we are talking with Bartlomiej Borzyszkowski. He's an AI research student working in cooperation with CERN Openlab, and his research might give us an insight into gravity waves and how our universe works. Bartek, welcome to the show.
Hello everyone. Hello, Bob. It's a great pleasure to be your guest. Please let me introduce myself. My name is Bartlomiej Borzyszkowski, and as you said, I'm a student of control engineering and robotics at Gdańsk University of Technology. And I specialize in autonomous platforms. However, my main research interests are decision systems, artificial intelligence, and robotics. I think it is worth to outline that simultaneously I work at Intel Poland, where I develop projects recently for Internet of Things group. I work on OpenVINO model preparation platform, as well as previously I worked on neural network processors and human body pose estimation for the Olympic Games. However, as you said, I'm really interested in international research. So this summer and last year during CERN Openlab program, I had opportunity to take part in activities organized by CERN.
Yeah, let's learn a little bit about that, because it's working with CERN, it's working on gravity waves, you're doing AI research. So at a high level, walk us through it. What is it that you're working on?
So the project I worked on is titled Anomaly Detection with Spiking Neural Networks, and we developed this project together with Eric Moreno from Caltech under supervision of Maurizio Pierini from CERN and Jean-Roch Vlimand from Caltech. So this is a part of bigger collaboration, but actually the research has started already a year ago when I developed a system of biologically plausible neural networks that aimed to classify elementary particles at CMS detector of CERN. So we were especially interested in neuromorphic computing thanks to its novelty in the domain of high-energy physics, but also different interesting features such as time dependency, which is especially useful in scenarios with time series data. So this year, our research was focused on LIGO experiments, and we took data from both raw detectors, from interferometers, as well as from simulation. And the project was followed on two parallel tracks. In the first scenario, we applied classical artificial neural networks and trained autoencoders for anomaly detection. In the second scenario, the approach was more experimental, and there we used spiking neural networks that were experimentally run on Intel neuromorphic research chip named Intel Loihi. In the first scenario, we accelerated our ANNs with Intel oneAPI, which was also greatly beneficial.
Yeah, you mentioned ANNs and spiking neural networks. Could you give me a little bit of insight into that? Are those the same thing, different things?
They are actually different things. Spiking neural networks are neural networks that are inspired by biology. The way how they work is different than using artificial networks, because here we rather depend on a signal that could have a different potential, and this potential terminates the activation of the neuron. There is a specific threshold, and the neurons activate when it is reached. So there are also different methods how to use these networks. We can either train them directly, which is more difficult because the signal is non-differentiable. Hence, we cannot use the classical approach such as backpropagation algorithms. There are also, of course, some approximations, but this is a challenging task nowadays. Another approach is based on conversion, and here also are different methods, different frameworks applied to convert such networks. In our project, we experimented with both approaches using conversion and direct training.
Well, fascinating. So spiking neural networks is more of hitting a threshold, and it sounds like it's closer to our own biology compared to an ANN. Would that be safe to say?
Yes, I think we could say so.
Yeah, it's absolutely fascinating to me. You're on the cutting edge, and you're working with CERN in LIGO, which is they're detecting gravity waves. And so how does this work play into that? What is it that CERN and LIGO are looking for?
This is a good question because anomaly in physics is always something different. So there is no one single answer to your question. One common thing is signal-to-noise discrimination problem. And here the aim is to discriminate, to eliminate noise, to filter it out, and to get information that is important for us for further analysis. And here, for example, CERN looks for elementary particles and tries to get as much information from detectors from Large Hadron Collider as possible. While LIGO, which we used this year, looks for events that happens in the universe by understanding gravitational waves. So these gravitational waves may be a result of, for example, black holes or neutron star merging, or maybe some rotations of stars or some explosions in the universe. So these events are very rare, and it is important to register them properly, so to make sure that we use our detectors as efficiently as possible. And this is why we wanted to propose a solution with deep neural networks.
Yeah, so my understanding is LIGO is a big sensor, and it's very sensitive, right? I mean, if a truck runs by the building that LIGO's in, the ground might shake. And so how do you know the difference between that and a gravity wave? So highly sensitive instrument. So understanding. So you're filtering out noise, so to speak.
Exactly. This is a very demanding task, and there are many techniques used for this purpose. Some techniques are taken from fundamental laws of signal processing. There are techniques such as Wiener's or Kalman's filters that are fundamental concepts used also in control theory, for example. Nowadays at LIGO there is a method named matched filtering that compares events that are coming to the detector with simulated waveforms, with a bank of simulated waveforms. And in our understanding, this technique could be a little bit limited to exotic events. So this is why we proposed unsupervised learning, where we learn our autoencoders that consist of different cells, for example, of LSTM cells with recurrent neural networks. And we teach them how to recognize noise. So we train them just on the noise, and then we give a signal from the detector that already contains injections with gravitational waves. And this is how we're able to distinguish them from actual noise.
That's absolutely fascinating. So are you on the training side then of this as well on the inference side in working with neural networks?
Yes, we did both, and we split our responsibilities in the project between me and Eric. However, we both worked on training as well as on inference of neural networks. There were different approaches used. At first, we trained our models, and when we were sure that there is accuracy that was satisfactory for us, that we reached this goal, then we started to experiment with SNNs using conversion and then using their inference on Intel Loihi chip. And on the other hand, we used Intel oneAPI for artificial neural networks, where we processed the model through HLS4ML library. This summer there was a backend designed by my colleague Marcin Świniarski. I also recommend to watch his interview from the project and his report. So together with Marcin, we designed this backend. I implemented their primitives in C++ that allowed us to accelerate our models for cross-hardware deployment.
Okay, so you got a lot going on with this particular project. You've got training, you've got inference, you've got a backend you're building, and it sounds you're doing that with oneAPI. So are these things all compatible? Are you just creating a lot of work, or are there some efficiencies involved in doing this?
In terms of oneAPI, we managed to run our models for anomaly classification, for anomaly detection through HLS4ML with oneAPI backend. And currently the project targets mostly CPUs. The reason was that it might be very useful for high-level trigger at CERN. However, it might be possible to extend it for GPUs, FPGAs, or other novel custom ASICs that might appear in the future.
Fantastic. So, like I said, you've got a lot going on, a lot of amazing work that you're doing with CERN in LIGO. Throughout this process, were there any standout moments for you, like an aha or something amazing or workaround that you figured out?
Well, yes, there were definitely many challenges in the project. And there were very difficult moments because we needed to explore the field. It wasn't like we didn't have straightforward tasks. We needed to explore the field to gain knowledge at first. It was also my first try with data from LIGO, so it was more experimental for me. I remember a difficult moment when we literally couldn't get any results from our SNN. The accuracy was very poor, and we didn't know what to do with Eric. So I started to debug the code, and after I think 2 days of hard debugging, we found that there was one threshold that was set too low, and it was blocking the signal of neurons that they literally couldn't spike. So after increasing this barrier, we were able to see the actual results, what was really exciting because it's probably the first attempt to use neuromorphic computing at LIGO ever. So the results of our project will be published soon, and I encourage to follow it.
Oh, yeah, that's amazing. You described kind of a very familiar situation that a lot of developers go through, right? Is you're banging on something forever and nothing's working. Then you realize there's just one thing that you got to change, and then suddenly it all works. And it's like you go from you feel like an idiot to you feel like a god. And so fantastic. That's absolutely fascinating. So where does it go from here, Bartek? What does the future hold for you and this project?
Well, I have a lot of different opportunities and plans for the future. Currently, for sure, I want to finish my master's thesis and finish my studies at Gdańsk University of Technology. Simultaneously, I plan to continue working at Intel because I'm really interested in the projects that we do, and I think that AI is a real future in technology in these days. In longer perspective, I will consider applying for PhD positions, but I still need some more time to think which narrow direction I would like to follow and which university I would like to choose. I'm also a great passionate of traveling, adventures and sports, so I'm looking forward to connect all of it.
Well, fantastic. You've got a solid plan, definitely a bright future ahead of you, Bartek. So thank you for joining with us.
Yes. One more thing that I wanted to add at the end is I wanted to thank Eric Moreno, who developed this project together with me. I would like also to thank my supervisors, Maurizio Pierini and Jean-Roch Vlimand. But I would also like to target great thanks to CERN Openlab for organizing this program and for the opportunity that I could join it. Also, thanks for Intel for supporting this project with technical on the technical part and expertise. So thank you very much, and thank you for the interview, Bob.
Excellent. Well, thank you, Bartek. Very well. That wraps up this show. If you like this content, then please follow the link below. Learn more about Intel oneAPI at the Intel Developer Zone. Also like and subscribe. And on behalf of a fantastic production crew, I thank you for joining us. I'm your host, Bob Duffy. We'll see you later.